All right, everybody, this is section 9.4, but before I start 9.4, I'm just going to refresh our memory from things from 9.3. The P series. P series looked like this. What was it? N, I think it was N1 to infinity. And you had 1 over n to a p power. If p was between 0, if p was between 0 and 1, including 1, this thing diverged. But if p was greater than 1, it converged. So we talked about that, I think, last time when we looked at it. That's the P series. And then we also looked at geometric series. And the reason why I'm just bringing this up, this is going to come up in this lecture. The geometric series, and from 0 to infinity, and we had a r to the n power. And here in the geometric series, if r was greater than or equal to 1, then this thing diverged. And if r was less than 1, oh, by the way, it's not only r, but it's the absolute value of these, then it converged. So these are from theorems from that section, 9.3. So in the homework, we'll be dealing with P series and geometric series, and we're going to be doing something called the comparison test. We're going to compare like a P series, something that looks similar to a P series, but it's not, but it looks similar to one. And we'll be looking at that. Yes, we are recording. Okay, so let's take a look at the PowerPoints. Get them up. Okay, so convergence test. So once again, we're going to be using the direct comparison test. Convergence tests that term of the series have to be fairly simple. And the series must have a special characteristics, blah, 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 blah. There's not much we really want to worry about here. I mean, you can read that. But we want to look at these things. This is a geometric series. But what happens if you have something that looks kind of geometric, but it has something else on top? So this is geometric. This is not. This is a P series test. This is not. They look similar, 1 over n to the third, 1 over n to the third. It's just extra stuff. It's this extra stuff that messes it up, that extra stuff that messes it up and doesn't make it exactly. And number 3, if you look, this can be integrated very easily since u is n squared plus 3. So the derivative of u would be 2n. And we could do that very simply, but this one is not. So what we're doing, direct comparison, we're finding things that are similar, like this is similar to a geometric series, but it's not, but we're going to compare them. This is similar to a P series, it's not. So we're going to do one that's similar to it and then compare it. So that's what today's all about. And so this is what we're looking for here. If B sub n, if this converges and it's larger then the other function or the other series, you see B sub n is greater than A sub n. If B sub n it converges, so, and it's larger, it has to be larger, then A sub n converges. And the same thing goes here if and they just say it the other way. If A sub n, if you know A sub n diverges, then B sub n diverges. So we're going to be looking at this direct comparison here in a second, but just know this is the direct comparison test. If one converges, then the other one converges. So let's take a look at this. So determine if this converges or diverges. So what they show you, right, once again, this is the geometric. This is a geometric. This is a geometric. There's R. But this is not a geometric. But they're so similar, we can compare them. We're going to use the direct comparison test. So if we look here, this is A, so we're calling this A sub n. And we're calling this one B sub n. And if you plug a number into both of these, let's just say you plug in n equals, something has to be greater than 1. Let's put any number greater than 1, let's 2. And when you plug that in, you get 3 to the second power is 9. 9 plus 2 is 11. If you plug 2 in here, you get 1 over 9. And if you look, B sub n, this number is larger than this number. This one's smaller if you compare these two numbers. So B sub n is larger. So we can use the direct comparison test. I'm going to come back up here. B sub n is larger. This was our geometric. So if I know B sub n converges, then A sub n converges according to this. So coming back down here. If we look at this function, it says it converges, but I mean, if you go back to your geometric series, the geometric series converges. Can somebody tell me what R is? I said R is 3, but I lied. What is R in this geometric series? Does anybody know what R equals in this geometric series? I said 3. I think I said 3, and that's wrong. I said 3 by mistake. But what is R in that geometric series? It's not 3. I don't know if you guys did the homework from last time. R is 1/3. This is the same thing as saying 1/3 to the n power. You take 1 to any n and you still got 1. And so there's 3 to the n power. So you can rewrite this as 1 to the n, 3 to the n, and this still becomes 1 over 3 to the n. So R equals 1/3. And if you look in the geometric series, if the absolute value of R is less than 1, then this series converges. So that's why they said this series does converge. This this converges. And since this is larger than this converges also. So we can say by direct comparison, A sub n converges. So that's what we'll be doing. I mean, that's it. We're looking at the simplified. I mean, this is, I'm going to say this is complex. And we're looking for at the simpler version of that. And if we can figure out if that converges, then the other one will converge. All right. So that's one, once again, direct comparison, comparing to and finding a simpler version. Next is the limit comparison test. If I divide the two functions, they both have to be greater than 0. If I divide A sub n divided by B sub n and get a limit where L is a finite limit and it's positive, then A sub n and B sub n either both converge or diverge. Just depends on what it does. I'm trying to pull this up because it's in my way. There we go. So that's all we need to know. If you divide the two and find a limit, then they both either converge or diverge. So let's see what that means. Here's a P-series test showing the following general harmonic. Show the following general harmonic series diverges. So we have to show this diverges. They want to show that it just diverges. So we're going to find something similar to that. If it lets me go to the next slide. There we go. And if you look, this is the function. And we're going to compare it to something similar. We're just going to compare it to 1 over n. I mean, it's the same thing. If pretty much, if you look at it, and we're going to divide the two. And I'm just going to go back. And they're just showing the more complicated one divided by the less complicated one, A sub n divided by B sub n. And so when we look at that, here's A sub n, my pen, B sub n, and we're dividing the two. And when we divide the two, I mean, you can look at it like this. I'm going to just do the division over here over A sub n plus B divided by 1 over n. When you divide two fractions, you change it to multiply and flip the second fraction. So you end up with n over A. You end up with n over A sub n plus B. Now, if you remember, when you take the limit according to infinity to find this limit becomes, since these are the same powers, like the horizontal the vertical asymptotes, then the limit becomes the numbers in front, the coefficients in front, 1 over A. A, we already said, was positive. And if you remember from a P-series test, why does it, let me write the P-series test again. 1 over n to the p. What makes a P-series test harmonic? That was a question from 7.3. What makes a P-series test harmonic? They call it harmonic. Instead of just outright saying a P-series test, they call it a harmonic series. By the way, it's also a P-series. It's the same thing, but there's a special reason why it's called harmonic. Did anybody read that in the book? It's because P equals 1. Anytime P equals 1, it means it's a harmonic. They call it a harmonic. It's still a P-series test, but it's harmonic. So when we look at this, if P is 1, we look at this. This is the P-series test. If P is 1 on a harmonic series, on a P-series test, if P is greater than 0, but less than or equal to 1, the series diverges. So that's why I wrote all that at the very beginning. So since this diverges, and we did get a limit, this diverges. So show that it diverges. So all you have to show is that it does have a limit, like we have here. We know this diverges, so this also diverges. So we're just comparing the two together. And that's pretty much what you're going to do over and over again in the homework. I think that was it for the PowerPoints. Yeah, that was it. So let's go to the homework. Give me a second. I should hit